Let's kick off this explainer with a pretty bold claim. The Multi-Layer Ceramic Capacitor, or MLCC, is literally the invisible hero of modern electronics. We are talking about the single most heavily produced component on Earth. Trillions of these things are manufactured every single year. They're absolutely everywhere, right? From the smartwatch on your wrist to the massive server farms routing your data, and yet you probably almost never think about them.
But you really gotta ask yourself, how do these tiny, practically invisible components solve the massive problem of high-frequency noise and power delivery drops in our miniaturized tech? Whether it's a 5G smartphone that crams literally hundreds of these around a tightly packed processor, or an electric vehicle's entire power network that needs uncompromised stability to keep you safe on the road, the MLCC is the unsung hero keeping all our modern circuits from just collapsing under their own complexity.
To really wrap our heads around how this component works, here's our agenda for today. 1. The unsung heroes physics. 2. Anatomy of an MLCC. 3. Cracking the datasheet code. 4. Layout rules and circuits. 5. Failures and common mistakes. And finally, 6. The senior engineer's playbook.
Let's jump into part 1, the unsung heroes physics.
Let's start at the absolute foundation. We need to look at the solid-state physics that makes such crazy high-density energy storage even physically possible. At the heart of this is the barium titanate, or BaTO3, crystal structure. Now, this is a ferroelectric material from the perovskite group. Because of the highly unique way it shares oxygen atoms in its crystalline lattice, it boasts a massive dielectric constant of up to 7,000 at room temperature. To put that sheer power into perspective, your standard industrial ceramics, they might only give you a constant of somewhere between 20 and 70. So this specific atomic structure is the absolute secret sauce for packing massive capacitance into the tiniest of footprints.
So how do we actually maximize this material? Well, just look at the core capacitance equation. It's basically a perfect balancing act of material science and geometry. By stacking more layers, that's the N variable here, and relentlessly shrinking down the dielectric thickness, the D variable, we can cram a huge amount of capacitance into microscopic spaces. That epsilon R in the equation, that's exactly that massive dielectric constant we just talked about. It mathematically proves that if you can print the layers thinner and stack a whole lot more of them, your capacitance is just going to skyrocket.
Moving right along to part 2, anatomy of an MLCC.
Taking this from theoretical physics over to the actual physical package, let's essentially crack one of these open and look at the internal construction. An MLC is really just hundreds of single-layer parallel plate capacitors stacked perfectly together. It's kind of like a microscopic club sandwich made of alternating ceramic dielectric and metal electrodes. Those internal metal layers, which are usually nickel or a specialized silver-palladium mix, act as tiny individual energy reservoirs. They're all connected in parallel, terminating at the outer metallic end caps that eventually get soldered directly to your circuit board.
And the manufacturing sequence to pull this off is just wild. This is how raw ceramic powder transforms into incredibly small monolithic packages. You start by taking a slurry, casting it into a flexible tape that's incredibly thin, we're talking as thin as 2 microns, and then you print conductive ink right onto it. Next, you stack hundreds of these printed sheets, laminate them under super high pressure, and fire the whole block in a kiln at up to 1400 degrees Celsius. This mind-boggling level of precision is what allows physical component sizes to shrink all the way from the chunky old standard 0805 packages down to the modern 00804 case sizes. And just for context, that is literally smaller than a grain of fine sand.
All right, part 3, cracking the datasheet code.
Because, let's be real, having a perfectly manufactured tiny component is absolutely useless if you don't know how to decode its datasheet. When you're building out your selection criteria, you really have to weigh the engineering trade-offs. Take Class 1 ceramics like COG or NP0. They offer extreme stability over wildly shifting temperatures and voltages, which makes them absolutely perfect for precise RF applications or highly sensitive timing circuits. But the catch? They have much lower overall capacitance. On the flip side, Class 2 ceramics like X7R or X5R give you a much higher capacitance density, which is totally crucial for power supply decoupling. But their stability fluctuates pretty wildly depending on the environment. You could literally have 2 capacitors sitting right next to each other on a circuit board that look completely identical, but they'll behave entirely differently based on their internal dielectric. Take a look at a standard manufacturer part number. Embedded right there in that simple string of characters is everything you need to know. The 0603 physical size, the X7R Class 2 dielectric, the 50-volt maximum rating, and the 100 nanofarad capacitance value. Honestly, skipping this decoding step and just guessing based on the physical size, that's a one-way ticket to catastrophic, unpredictable circuit behavior.
Which brings us to part 4, layout rules and circuits.
Let's bridge the gap here between selecting the component and actually putting it on the PCB, specifically when we're dealing with high-speed digital circuits. Imagine you have a modern FPGA. If that chip needs to instantly gulp down a massive 50-amp transient current in less than a nanosecond, this target impedance equation proves exactly why your power distribution network has to be utterly flawless. To keep the processor's core voltage from entirely collapsing outside its tight tolerance window, your network impedance often has to stay well below 1 single milliohm. And the MLCC? That is your primary frontline weapon to achieve this ultra-low impedance.
But look, an MLCC only works if you actually place it correctly. To maintain that crucial ultra-low impedance, junior and senior designers alike absolutely must memorize these strict layout rules. Why? Because every single millimeter of PCB trace length adds about 1 nanohenry of parasitic inductance, which basically acts like a choke on your fast current delivery. You have to place these capacitors incredibly close, just 3 to 5 millimeters from the IC power pins. You want to use a 2x2 via configuration to effectively cut the inductance path in half. And you must absolutely never ever share vias between adjacent capacitors.
And since every single capacitor carries that unavoidable parasitic inductance, they all eventually hit what's called a self-resonant frequency, or SRF. Above this specific high frequency, the capacitor actually stops acting like a capacitor and starts acting like an inductor. This is exactly why we use a multi-capacitor strategy for wideband decoupling. We pair a bulky electrolytic for the low-frequency bulk energy with a 0.1 microfarad MLCC for the mid-range decoupling and a tiny 100 picofarad MLCC to handle the ultra-high frequencies. When one capacitor hits its SRF and becomes inductive, the next one seamlessly takes over the job. It's essentially a high-speed relay race of capacitors, making sure high-frequency noise is always suppressed. Moving on to part 5, failures and common mistakes.
Even with perfect layout geometry and flawless math, things can and definitely do go wrong in the real world. Allow me to introduce the silent, devastating enemy of your design, the DC bias effect. If you buy a 10 microfarad Class 2 ceramic capacitor and hit it with a continuous DC load near its max rated voltage, it might dynamically drop to just 2 microfarads. Why does that happen? Because the intense electric field literally locks up the atomic structure of that barium titanate we looked at earlier, physically preventing it from storing any more charge. This specific phenomenon catches so many otherwise brilliant designers completely off guard.
And it actually gets weirder. Because these Class 2 materials are ferroelectric, they are also inherently piezoelectric, meaning varying voltages can cause the physical ceramic package to rhythmically expand and contract. This microscopic mechanical movement can actually vibrate your entire circuit board like a speaker cone, creating this highly audible, really annoying high-frequency noise. In the industry, we call this phenomenon singing capacitors. Even worse, in extreme mechanical stress environments, this continuous flexing can lead to micro-crack failures in the brittle ceramic, which can eventually short out the entire board and cause a complete system failure.
Finally, part 6, the Senior Engineer's Playbook.
So how do industry veterans proactively avoid these traps in hypercritical products like life-saving medical devices, aerospace flight controllers, or high-voltage electric vehicles? Well, the pro mindset requires a rigorous, totally non-negotiable checklist. Seniors will constantly derate the operating voltage by 2x or even 4x to aggressively fight off that DC bias effect and ensure long-term safety. They don't just skim a datasheet's front page. They dive deep into the specific ESR and ESL frequency response curves. And if they're designing for an EV, they strictly mandate AEC Q200 automotive-grade parts and utilize specialized flexible terminations, often using internal conductive epoxies, so everyday road vibrations simply cannot crack that rigid ceramic.
There is a great saying in the industry that perfectly sums up our engineering journey today. The art of capacitor selection lies not just in knowing the formulas, but in understanding the subtle interplay between electrical parameters and real-world application demands. Theoretical physics and basic classroom equations only truly matter when you deeply understand how that tiny, seemingly insignificant grain of ceramic actually behaves on a fully powered real-world board under intense thermal stress and high-frequency noise.
So as you approach your very next PCB design, system analysis, or power delivery network, you really have to ask yourself, are you truly optimizing your power distribution, or are you just blindly guessing the capacitance? Don't let the unsung invisible hero of modern electronics become the invisible, untraceable point of failure in your product.
Do the math, respect the underlying solid-state physics, carefully decode your datasheets, and stop guessing. Thanks so much for joining me on this explainer. I'll catch you next time.